Hello everyone, welcome back to this channel, and in this video we're going to look into chapter 6 of IGCSE physics called energy. And here is the chapter overview. Energy, in a written definition, it is the capacity to do work or cause change in a system through various forms. So we have two different types of energy. One is energy stores and energy transfers. To give you an example of how it works in real life, so here it is. Let's say you're running, and before you started running, you need energy in your muscle, which is usually stored under the fatty tissue. And if you learn biology, you know that this will help your cells to carry out some function that will help you run. So the energy that is stored under your muscle here is the chemical energy. And as you start running, the energy will be converted into kinetic energy plus a little bit of thermal energy. It's when you sweat and you feel a little bit hot. So that's how energy in a real example can exist in different forms. And in our example just now, the chemical energy and kinetic energy, they are called energy stores because they are energy inside an object or a person here, whereas energy transfer is more like energy that's being transferred. So here are the different forms of energy. We have kinetic energy, which is energy inside a moving object. The faster it moves, the higher the kinetic energy. The second form is gravitational potential energy, we usually call it G.P.E. And it's the energy of an object raised up against the force of gravity. So look into this pen here. If I were to release my hand, it's going to fall down because due to gravity. But I can lift it up, I can hold it. And now this object, it is acting against the gravity, it's not falling down. So we can say it has a gravitational potential energy. And the higher the object is, the greater its G.P.E will be. Next up, we have chemical energy. The energy stored in bonds between atoms. If you learn chemistry, you will know this. That can be released when chemical reaction take place. All right. In the running example, the chemical energy is stored in your body. Next up is on nuclear energy, which is the type of energy stored in nuclear fuel, like uranium. Strain elastic energy. So this is what we learned in the last chapter. We know that as an object is stretched, and when you release it, it's gonna exert some force on it. So meaning they also have some energy inside it when it is being stretched or squashed. Whereas internal energy, next one, is the energy of an object itself, the total kinetic and potential energies of the particles. In fact, the internal energies could be the energy inside an air particles, so on and so forth. Thermal energy, self-explanatory, energy transferred from a hotter place to a colder place because there's a temperature difference. Electrical energy is the energy carried by the movement of electrically charged particles, which we'll learn more about it when we are in the electrical chapter. So here are a list of energy stores and a list of energy transfers. So there are different ways which energy can be transferred. So if we look at this person here, he's doing lifting. He's basically giving this dumbbell or barbell here some gravitational potential energy. So energy can be transferred by force, or you can look at this little girl here when it's moving something. It's actually giving this box kinetic energy. So that's how we transfer energy, let's say chemical energy inside the body, to kinetic energy into a box. First method, by force. Second method is by heating. Is when energy from this, let's say hot coffee, is transferred to the surrounding. So that's when energy is transferred from a hot object to a cooler surrounding. Also by radiation, so sun energy here is being transferred to the earth via radiation. And some of the energy is transferred via infrared or an ultraviolet radiation. So also the next one, which is one of the most effective method to transfer energy, is by electric current. So electricity, let's say it's the one that is generated in a hydroelectric dam, can be transferred effectively using electric current via these transformers. So let's look into one quick example. You will sometimes be required to draw this. Draw the energy flow diagram for using a flashlight. So we know that if the flashlight works on battery, first we have chemical energy inside the battery, and then being converted to electrical energy, and also at the end, internal energy of the torchlight. And this torchlight will exert light energy to the surrounding, at the same time also heat energy. So that's how you draw a energy flow diagram. And another way you can express the energy flow of something is by using an equation. Let's say, what is the energy transfer on a rocket launch? So at first we have chemical energy stored in the fuel, transferred to kinetic energy, which causes the rocket to move, plus G.P.E, which causes the rocket to move a little bit upwards, plus thermal, heat, light, and also sound, the engine sound. So that's all about energy. Let's look into one law called the conservation of energy. So what this law says is that energy cannot be created or destroyed. It can only be stored or transferred. So if I were to lift this pen up, we know that it's gonna have G.P.E, but the moment I put it down, it's gonna fall. And it will gonna lose some of the G.P.E. But that G.P.E will not be just disappeared. In fact, it will be converted into kinetic energy because it causes the pen to move. So that basically shows conservation of energy. You can't really destroy or create an energy. You can only transfer them. So another example is this ball on the mountain here. It's gonna have a little bit of G.P.E, but if we were to exert some push on it, it's gonna fall down, and G.P.E of it will be lower because now its altitude will be lower. But that doesn't mean the energy is lost. It's just that the energy is now converted into another form of energy. In this example, kinetic energy. So when it comes to this energy transfer, we always need to find out where does all the energy goes, because they won't disappear, and it's important to know where they are being transferred to. So let's look into this book example. A car burns 3 times 10 to the power of 5 joule of fuel per second. So that's chemical energy. And it has this amount of kinetic energy and this amount of G.P.E. And how much energy transfer away from the car through thermal energy. So this is very simple. We know that what is being provided is 3 times 10 to the power of 5 equal to the kinetic plus the G.P.E, which is 0.7, which is 10 power 5, and therefore plus heat. So in order to find heat, we just have to use the energy provided minus kinetic and minus G.P.E, which will get this answer here. All right, so I believe we have one more zero here. Sorry for the typo. So 100,000 joule is lost through thermal energy. So let's look into another diagram here. This is called a Sankey diagram, which will show how energy is being transferred effectively, because again, energy cannot be lost. So initially you have chemical energy, some of it being transferred to kinetic, thermal, and also sound. And the bigger the width of the arrow represent the amount of energy contributed to that particular form of energy. So in this case, we have most of the energy converted to kinetic. So there's one video that I think all of you should watch, which is from the professor Walton Levin. He basically shows you the conservation of energy in a very engaging manner. So the link is in the description, so feel free to watch it. Now, let's look into another subtopic called energy efficiency. So now, let's say you have a car engine. Not all the energy provided by the engine is going to be converted into kinetic energy. Some of it will be lost through heat. And that the heat is a result of frictions or air resistance. Some of it could also be the sound. So definition of efficiency. That fraction of energy supplied that is usefully transferred. Meaning, if I contribute 100 joules of energy, how much of it is going to be contributing to the useful purpose? So here we have the typical efficiency for different equipments. You can see that electrical heater has the highest efficiency because most of it is being transferred to heat energy. So again, we have another formula, efficiency and percentage efficiency. They're basically the same. It's just that whether you multiply the equation by 100%. It's calculated using the useful energy output and the denominator and the total energy output in the denominator. So let's look into an example to understand it. A tidal power station expected to produce 33 terajoule of energy when the tides provide 100 terajoules gravitational potential energy. What is the efficiency of the power station? So efficiency is useful energy output using the one that is provided. So we know that the G.P.E of the tidal power station 100 terajoule, but then only 32 terajoule of it is being used for useful purposes. So therefore we can say that if we were to cancel everything out, the efficiency is 0.32. If you look into the answer, that's what we get. Meaning the efficiency is not very efficient. In fact, 68% of the energy is basically lost to somewhere else. So let's look at another example. A filament lamp is 4% efficient. So now they use a percentage sign. How much electrical energy must be supplied to the lamp each second when it produces 6 joules of energy light per second? So the useful energy here is 6. But then we don't know how much is we need to provide. So this is going to be unknown. And multiplied by 100% because they are using the percentage sign, which will be equal to 4%. All right. So if I were to pull everything into the other side, so I'm going to 6 over E versus 4 over 100. We're going to have 4E equal to 600 and E will be equal to 150. So 150 joule will be the amount of energy we need to provide. So if you look into the equation here, so that's how I solve it. So let's move on to the very specific type of energy, G.P.E and kinetic energy. So these are the only energy which they have a formulas, and you can calculate basically for this moving object how much energy is in it. So let's look into first thing, the G.P.E. As I said, gravitational potential energy is the energy which when an object has when it's lifted up to somewhere. So in this example will be this vehicle. And there are three factors affecting G.P.E. The height, the mass of the person, and also gravitational acceleration. And this will be different in different planets. So the formula to calculate G.P.E, simply to use the mass of the person here, then gravitational potential acceleration, and also the height of the person. And do know that we only care about the vertical height. So if the hiker is here, we only care about from here. So it's the vertical height from object, and we only consider the height of the object's center of gravity. All right. So let's look into an example. An athlete of mass 50 kilogram runs out a hill. The foot of the hill is 400 meter, and the summit is 1,200 meter. By how much does the athlete G.P. increases? Assume that acceleration due to gravity is through 10 meter per second square. So here I have an illustration. It's important to draw this diagram out in your exam because sometimes it's very hard to picture what's happening here. And initially the hiker is over here and then he moved up. I know it's not a really realistic diagram, but it does the job, right? So that's how we solve it. Okay, we will calculate the initial G.P.E of this person. The G.P.E is calculated using the formula mgh. And the mass of the hiker is 50 kilogram and G is 10. And its initial G.P.E, use the initial height, 400 meter. So if I plug this into the formula, I can get 20,000 joule. So that's for initial. And the final G.P.E will be when the hiker reaches the peak. So the same mass, 50, multiply the same gravitational acceleration, just a different height now. So if I were to plug everything into the equation, I'm going to get 500 multiplied by 1200. I'm going to 60, 1, 2, 3, 4 joule. So to show you the equation, the solution here. So I believe I make a mistake again from calculating it. Yeah, so this one should be 200,000. So the change in G.P.E, if we compare the initial G.P.E and the final G.P.E, is 600,000 minus 200,000. We got 400,000 joule in the change of G.P.E. So that's all about G.P.E. And let's move on to kinetic energy. So a moving object is stored of energy. This energy is known as kinetic energy. So it means if this car is moving, meaning it has kinetic energy. And there are two factors affecting kinetic energy. The mass of the object. We all know that if, let's say, an elephant is running towards you as compared to a cat, the energy is going to have more kinetic energy than the cat. So mass is important. And second one is speed. You mean the faster it moves, the more kinetic energy it has. And the formula to find the kinetic energy is using 1/2 multiplied by m times v squared. So let's solve some question. A van of mass 200 kilogram is traveling at 10 meter per second. Calculate its kinetic energy. So k dot E equal to 1/2 mass times velocity squared. So I'm just gonna sub all the values in, and I'll have 1/2 200 multiplied by 100. So I'm gonna have 10,000. So 200 times 100, I'm gonna have 20,000 divided by half. I'll get 10,000 joule. So there's will be a kinetic energy. And when the speed increases, it's being increased to 20 joule of energy. By how much does it increase? So I just have to change this into 20, and I'll have gotten a different result. And to show you the full step, this is the initial kinetic energy. This is the final, and you will use 20 here, and the change will be 30,000 joule. So let's solve some positive question before the end. The figure shows water flowing at very slow speed and the waterfall at 50 meters over the rock. Show that the velocity of the water when it strikes the rock is 17. So that's a pretty vague question. They didn't really give it anything. But this is also a very common question in this chapter, which you need to understand that in this scenario, initially the water will have gravitational potential energy. And as the water flows down, all of this G.P.E will be converted into kinetic energy. And that's when two equations should be put together. So meaning mgh of the water as it flows is going to be equal to half mv squared, which is the kinetic energy of the water. And using linear equation law, I know that I can cancel the m out, so I don't have to know basically how heavy the object is. And by using this equation, GH equal to half v squared, and what I want is v. So I'm gonna go v. I'm gonna move 1/2 to the other side. We'll have 2GH. And I'm gonna move the square here to the other side. It's gonna be square root. And to find v, to show that v is 17, I simply plug in all the values I have. 2 multiplied by g, which I will use 10 here for simple sake, and h, which is 15 meter. I'm gonna get 20, 30, so 300. And if I plug 300 square root 300 into a calculator, you should get 17 point something meter per second. And that's how we show that the velocity of the water is 17. If we look into the answer, this is what you'll get. Assuming I'm using G 9.8. And if I plug everything into the calculator, I'll get the answer here. And that will show that the velocity is 70 meters per second. So let's solve another question on how the two, mgh and half mv squared. We have a very happy question here. When a salmon swims up a river to breathe, it often has to jump off waterfall. The figure shows a salmon jumping above the surface of the water, and it falls back down to the river. So key information, the salmon has a mass of 2 kilograms, and it leaves the water with kinetic energy of 16.2. Calculate the speed of salmon. So we know that kinetic energy formulas is, let's write it down, half mv squared. So I'm going to have 16.2 as my kinetic energy, 2 as my mass. I'm going to care only about the speed. If I move everything, so I cancel this out, I'm going to get 1 v 2, 3. Yep. So I'm going to get 1/2 multiplied by 2. I'm going to get 1. So I'm going to cut it. So v2 is 16.2. V is equal to square root 16.2, which will be equal to 4 point something. If we look into the answer, yeah, you're going to get 4. All right. So another question. This is one that is very similar to the waterfall question. Calculate the maximum height gained by the salmon. We know that the fish lift the water with a kinetic energy of 16.2. But then, as the fish reaches the peak of, wherever it can reach, it will start moving. And all this kinetic energy will turn 0. And it will all be converted into G.P.E. So in other words, I can use 16.2 here. It is also the G.P.E of the fish when it stops moving, according to the principle of conservation of energy. So I'm going to do 16.2 equal to maximum height. So the G.P.E formula is mgh. So 16.2, the mass of the fish is 2 kilogram, and G is, let's use 10, and we're going to find a H. So it's going to be 16.2 divided by 20. And if you plug that into the formulas, you should get the answers 0.81 according to the marking scheme here. All right, so in this question here, a large truck of mass 5,000 kilograms is traveling at 5 meters per second, and a mass motorbike has a mass of 200 kilogram, and they need us to find out what is the speed of the motorbike. So we know that both the kinetic energy of both truck and the motorbike will be the same. So we can write down the equation. The half mv square of the truck is equal to half mv square of the motorbike. So for a truck, I can use 5,000 as my mass, 5 as the meter speed, and it's half. This motorbike is 200. What I need to find is the velocity. So if I plug everything into the equation, I'll get v square. I can basically just use this 1,000, 5 square, divided by 1 over 2, 200. So if you put everything into the formulas, you should be able to know that 25 is the answers. All right. So next question. The diagram shows an LED light bulb. Which expression gives the efficiency of the bulb? So 8.0 watts is the input power. 7.5 went to the light energy, which is the useful energy, and 0.5 is the useless one, the heat loss. So to find out the formula, remember it's useful energy divided by energy provided multiplied by 100%. So if you look into, so this is exactly the same as option D. So my answer is D. Right, so let's move on. Next one, which action requires the greatest power output from the fault plate trough? Even though we haven't learned the topic power yet, but then one way we can solve this is that we just check out which, so we have two conditions here, whether it's high or low, all right? And then it's whether it's slow or quick. And we know that this question involves G.P.E and also kinetic energy. The higher the G.P.E and the kinetic energy, the more power you will need to put it up, right? So in order to have requires the greatest power output, we need it to be at the high position and at a very fast speed, because the height and also the speed are the two factors that affect G.P.E and kinetic energy. So my answer should be lifting the box from the ground to the high shelf very, very quickly. The answer is B. So the last question of this video, the diagram shows a model of a wind turbine used to demonstrate the use of wind energy to generate electricity. And the mass of the error is 7.5 kilogram. And the kinetic energy is 240 joule. And it's pretty simple. We just use the kinetic energy formulas. Half mv square. Kinetic energy is 240. Go to 1 over 2, 7.5 v square. And I can just move v squared as my subtract. 40, 1 over 2 times 7.5. And again, if I were to plug everything into the formulas, I should get the value 8 here. And that's how I solve this question. And that's how the chapter is all about. So in this chapter, we basically learn about the different types of energy available and the principle of conservation of energy. And we also delve deep into how to calculate G.P.E and also kinetic energy. So I hope you learned a lot from it. We'll talk more about energy in the next video. Thank you for watching.